Welcome to our distinguished lecture today with Alexander Glaser. Thank you very much for being here. And thank you very much for being here as well. My name is Marike. I'm from the CASA office. I organized this lecture today. And I also brought some CASA merch. If you would like to take some in the end, feel free to. I also brought an attendance list. It doesn't ask crazy info, just your name so that we know how or who visits our lecture. So please write down your name there, and then I pass over the mic to you. And yeah, thank you.
Okay. Thanks, Marike, for the nice introduction. Yeah, so yeah, it's our and my great honor to have Alex here, Alex Glaser. We've I think you or Sebastian reached out to us many years ago, and we have a very extremely cool ongoing research, mainly through Johannes, my PhD student, and he's doing extremely, I would say unusual, but extremely cool work from a security perspective. So he has a very extreme application for security, namely nuclear arms control, which has unbelievable, nice, interesting problems related to security, this interaction also with digital security and cryptography, but also with hardware security, which is a topic that my group loves to work on. And already this morning, I think we came up with like 3 different areas we should jointly investigate. Yeah, and we're very much looking forward to your talk, and I think that will be much food for thought for our MPI here, and of course to CASA. Thanks for coming, Alex.
Okay. Okay. Well, thank you so much, Christoph, for the introductions, and of course also the invitation in the first place. Thanks to everyone for coming, for joining here in the room, and maybe even online. You can see that the title, Keeping Nuclear Secrets at a Distance, New Approaches to Nuclear Monitoring and Verification, which is sort of my bread and butter sort of work, but as Christoph mentioned, we think there's actually some real some opportunity to collaborate with your community, and hopefully in the best case that we have 1 or 2 ideas sort of following this seminar, how this could look like. Let me, it's the old Zoom problem, perhaps say just a word or 2 about who I am, where I'm coming from. You can tell from my accent that I originally do come from Germany. I'm from Darmstadt, but I spent the last 15 or 17 years at Princeton University, where I now co-direct a program called the Program on Science and Global Security, which has been around for more than 40 years. And so you can see sort of the current members, and essentially we are a group of students, researchers, and faculty working on science and global security issues. We tend to take a technical approach or provide technical analysis to support policy in this space. I actually felt, this is essentially a screenshot from our website that I think sort of hopefully captures the essence of what we do. If you look at the top here, you can see there's the program, which is our team. We also have a small laboratory where we conduct simple experiments and build prototypes. There's a laboratory, a bigger DOE laboratory across the street, the Princeton Plasma Physics Lab, where we then try out some of this equipment in a different environment. We also have a journal, which is called Science and Global Security, and it's sort of the only peer-reviewed journal sort of dedicated to work in this area, and has been published since 1989. So what are we working on? You can see at the bottom here some areas that we tend to emphasize. There are a lot of emphasis on nuclear issues, which never quite seem to go away, and unfortunately are coming back now. Verification is a big part of my own work, and this is really what I will focus on today. And there's a couple of other technologies that are relevant for what we do. So real quick, background. Again, most of my comments today will be on nuclear issues. So let's just have a very quick look at the state of the world, so to speak, today. As you know, there are several thousand weapons that still remain. Most of them are owned by the US and Russia, but then there are also seven other nuclear weapon states. Of course, these numbers have come down dramatically since the end of the Cold War, but they've sort of settled at this level now. And for the very first time, quite frankly, since 1990, there's now a real possibility that these numbers might actually go back up again, which is something that I personally could not, or I think no one could have anticipated even just a few years ago. In terms of, the consequences of nuclear weapon use, I don't want to spend too much time on this, on the details, but clearly, and as you all know, the use of a nuclear weapon would have catastrophic humanitarian consequences, especially if they are used in urban areas due to the blast effect, the thermal radiation leading to fires, but also the radioactive contamination. There's both prompt and delayed nuclear radiation leading to fallout. And even if, obviously this is coming back now in the context of the war in Ukraine, even a very small nuclear weapon would be qualitatively different than anything else we've seen since 1945. And obviously you would contaminate, not only destroy, but also contaminate an area for years and probably decades to come. So this is, I think, very relevant, unfortunately. There's also a real concern and a real risk that any nuclear weapon use, even sort of a small single use, could escalate to a major crisis, a major thermonuclear war, given how these postures are set up. A couple of years ago, I think in 2017, we put together a little video that we posted on YouTube at the time. And unfortunately, this is quite a popular video right now. And if you look at the sequence that we sort of describe, it's very similar to what folks are really concerned about today. And I think the video now has more than 3.5 million views or so. But again, not something we anticipated. That said, there are efforts underway, not only in our program, but in many different places. And I do want to emphasize that the German government has actually contributed to both policy and analysis, but also technical research in this space. Malte Götze from Aachen and I, we put together a little primer or a book just last year where we sort of describe and summarize some of the current opportunities and challenges and how to make progress toward nuclear disarmament. And again, with a specific focus on the verification challenges that would come along with it. And again, even, progress is not going to happen this year, certainly not, and maybe not in the next year either, but clearly in the longer term, hopefully we'll get back on track and we'll have agreements that require verification of certain limits on the arsenals. Unfortunately, I just want to sort of end with this sort of on the policy side. There are, these are difficult times, and as most of you here in the audience know, German government just assigned another 100 billion euros to modernizing the Bundeswehr, the armed forces, and that package would include, for example, these new aircraft, the F-35, which is certified to carry and deliver US nuclear weapons, and some of them are here in Germany. So this would be several $1 billion that would go directly to these aircraft. And there was a hope not too long ago that perhaps Germany might actually choose a different type of aircraft and would slowly and gradually abandon the reliance on these US nuclear weapons, which would be delivered by German pilots in the event of a crisis. But let me leave the policy side of things for now and focus more on the technical challenges. Both of them are obviously relevant, and the question, how can we enable reductions in the nuclear arsenals once they become, politically feasible. That's really what I spent most of my time on. So let me say 2 or 3 things about, nuclear weapons. What are they? And this is very high level, and we don't really have to know much anyway. But obviously, they are highly classified items, and I get back to that in a minute. But we do know that they contain fissile materials, in particular plutonium and uranium in kilogram quantities. They typically are, in two different parts of the weapon. And since these materials are radioactive, we can use these signatures to detect and also confirm the authenticity of a nuclear weapon if we, for example, want to dismantle it. So that's sort of part of the challenge. We want to work with equipment that can identify nuclear weapons. So this is what we know. This is how they look like. Here's another photo. You get the same idea. Even North Korea has now weapons that have these 2-stage design, and it's sort of very obvious here if you look at this picture. And this is a photo that North Korea published a day before they actually detonated its largest nuclear device in 2017. And it's quite surprising that they had such an advanced design with so few tests, and they may have had some help. We don't know. As I said, a lot of things, or almost everything about nuclear weapons is classified, but and that's not going to change. Here's a small exception, and I do have to sort of show this because I find this really as a remarkable thing that happened back in the late 1980s. This was even before the Soviet Union, fell apart. Gorbachev sort of reached out and wanted to do things differently, invited a couple of US scientists to come to the Black Sea and conduct this experiment and make measurements on a Soviet nuclear weapon. They later, actually, this in the middle with the red shirt is someone who's still very active in this field, Steve Feder, published a paper in Science magazine having this very detailed gamma spectrum, which essentially gives you everything to reverse engineer this device. The Soviets were not too pleased, but there was a real push at the time to be more transparent and more open about things in this space.
Would another warhead have a different signature specific to one specific warhead?
Well, so the question is, how unique is this signature? Again, this is classified. I don't have any clearances. So, but the idea is that you can clearly identify the type of nuclear weapons. You can probably read much more out of this. From what I understand, a weapon designer can essentially reverse engineer exactly how the weapon looked like, and that can help you sort of defeat it if you think you have to. In any event, these days are over. We're not going to see anything like that anytime soon, probably never. Just for completeness, I want to mention, it's sort of ironic that this measurement was made on the Slava, which was later renamed the Moskva, which, as you know, was sunk just a few weeks ago. Sort of the irony of that is sort of not lost on us, I guess. Okay, so how do we deal with secrets then? I mean, if this is not the way this can be done, we have to do it differently. Here are some early ideas. So the idea was, okay, if we can't publish these spectra, we have to develop information barriers. We have to somehow remove that information. And the first efforts, and I hope you find this somewhat amusing, I don't know, was to build just a big device with cabinets and so on. And you see all this sort of junk in the closet on the left, and probably ran Windows 3.1 or something, and then only display sort of the irrelevant information at the very end, green lights and red lights. And so if the weapon was real that you wanted to measure, everything turns green. If you see a red light, you have a problem. And that was sort of the original idea. We measure something and then we remove everything that we don't want to release. Sure enough, when the Russians actually saw that, and they came to Los Alamos in the early 2000s, they said, all I see is a green LED with a battery connected to it. And I hope that sort of resonates with you in the audience. So why is it so hard to do this right? And let me sort of just put out a few constraints on the problem. Number one is, and as I said before, very little is known about the inspected items. So imagine you have to develop a system and a piece of equipment, but you don't know what you're supposed to measure. I mean, that is sort of fundamentally, of course, a problem. Maybe some information maybe shared in advance. You know, probably there's a kilogram or at least a kilogram of plutonium. Okay, so you can detect, you know, gamma radiation and so on. But certainly you're not supposed to learn anything else during the inspection or the measurement. So that's number one. Your adversary or competitor has de facto infinite resources. You have to sort of assume that, right? We're talking US, Russia, China, you name it, and you make assumptions about their capabilities, real or imagined. So that's the second challenge. And you may have to assume that your adversary is really, you know, motivated to deceive you. Number 2 and 3. And then finally, typically the assumption is that the host has last ownership of the inspection system before the measurement. And you think, oh, yeah, that's not going to be great. And the inspector will never see the machine again once it has been exposed to classified information after the measurement. So you're not allowed to look at this thing before or after. And I hope there's some skeptical, you know, sort of responses here in the audience. So that's traditionally the setup. Yeah.
Has this setup ever been utilized?
No, I mean, this has not been. This is the challenge that our community is sort of working with, or this is the starting point, right? And we can challenge it. I mean, obviously, for example, you would say, well, maybe we should really develop the system jointly, and maybe we do some cut and choose. You know, we have 7 systems on the table. We use one for the inspection, and we can disassemble the others. You had some randomness, but to what extent this really makes you happy in terms of, you know, are there hidden switches, side channels, you name it, is sort of a separate question.
This problem is different than, I don't know, human inspectors going to higher up and whatnot.
It is different in that sense. It would be a good question. In the case of Iran or other countries in the civilian space, let's say, there is the International Atomic Energy Agency, the IAEA, based in Vienna. They have the authority to, you know, they bring their own equipment. And if you're Germany or Iran, or you sort of can't ask for, you can't use your equipment, there's sort of a different power balance. The problem here is it's US and Russia. There's no trusted third party. We have to sort of sort this out between us. Good point. Okay, so how do we approach this then? Okay, what are the options? So I have 3 proposals, and let's see what they are. I mean, the option 1 is to just keep going, and let's just improve the electronics and the approaches we have in the community. This is called, you know, certifying the equipment and authenticating the equipment, essentially trying to make sure that there are no side channels, there are no hidden switches. You know, it's actually doing what's supposed to do. Their equipment. No. But you know, the labs, they can build equipment. You know, we build equipment. This is actually one of our devices. I mean, you can build it. It's never going to be used, or it hasn't been used. Well, you can build it. You're just not allowed to use it on anyone's devices. Second one is to sort of reinvent the problem, and I will spend the next 15-20 minutes or so emphasizing this point, just to be honest about that. And the idea fundamentally being, you know, if it's so hard to protect the information, perhaps it's better to never actually acquire the information in the first place. And you know, if you don't know the secret, you can't lose it. That's sort of the idea. And again, I won't read here the detail, but that's basically what I'm going to discuss in the next couple of minutes. Third, option is to reveal the secret. And I always want to add this to the menu, because I do think it's important. I mean, some of the complication is really due to the fact that certain things are classified. If you reveal the secret, again, you can't lose it, right? If there's no secret, you don't have to worry about it. So if the weapon states agree to release certain types of information, then you can actually, you know, pursue very different measurement approaches, and you know, things might just get much easier. But obviously, that's not something we can demand or ask for. But I do think it's important to have this sort of on the map as an alternative to simplify the problem.
Question, that's my naive. Is this because you states to be able to build weapons this way, or is it that even, I don't know, Russia would be able to build similar kind of?
Right. So the question is, why is it secret? Again, it's not for me to sort of make that call. But fundamentally, I mean, there's a few scenarios. One is, let's say, so I mentioned earlier, there are 3 to 4 kilograms of plutonium, we assume, in a nuclear weapons. Let's say it turns out there's only 1 kilogram of plutonium actually in the weapon. If you are sort of another weapon state, you realize, what? They only use 1, we use 4. There must be another trick that we're missing. And suddenly you can make, with the same amount of fissile material, you can make 4 times as many weapons, right? So that's one part. But there's also, if you try to defeat one of these weapons, again, I don't want to get too far off track. So let's say there's a warhead coming in, you're trying to shoot it down by, let's say, detonating another nuclear weapon to overheat this device. If you have an idea how this weapon is designed, you may sort of know what exactly you need to do in terms of how many neutrons you have to sort of shoot at this thing to make it essentially melt inside the cone instead of before it detonates. I mean, that's sort of two very sort of random high-level ideas of why this is classified. There's another question, yeah.
What is the control part? What are trying to control? Is it the fissile material or is it the weapon part?
Very good questions. I have more on this coming up. So the question was, what am I trying to do here? What is controlled? It depends on the treaty and we don't know what that treaty would look like. The treaty could, for example, limit the amount of weapons that you're allowed to have. Yeah, let's say you're allowed to have, 2,000 warheads, and there would be inspections, and we walk in, and we would start somehow accounting for your the weapons. We try to count them. Let's say you want to dismantle some. You say, okay, today we have to get rid of 100 because that's based on our schedule. And you roll in a container. I want to make sure, is this actually a nuclear weapon or is it just a pile of rocks, right? So I have to make certain measurements to make sure I'm confident that whatever you're showing me is a nuclear weapon. Eventually I want to recover the fissile material, etc. That's sort of further downstream. But I do typically want to make sure that whatever you showed me was actually a nuclear weapon and not something else that you had in the basement. Okay. I see some skeptical. Okay. Yes, I think I promise you I have a few more things coming up. Okay, so let me give you a few examples. I think I have 3, and to illustrate some of the ideas and concepts that we've been pursuing. This one perhaps is a bit not as interesting for this community, and I tried to keep it short, but that's sort of how we started. It's pretty much, it's still what we're doing, and we're actually doing experiments, and it did generate quite a sort of a steer in the community where sort of new attention focused on this. We said, okay, if the problem really is due to the electronics, the fact that we can't trust the electronics in the first place, maybe we should remove the electronics from when things are actually sort of happening, sort of from the key moment of the inspection process. I mean, there would be electronics in other areas, that's fine, but we wanted to remove it from the measurement process, and we went back very old school to non-electronic detectors. I mean, that's one option to approach this, and I just want to mention it at least briefly. In this case, we detect neutrons, and the physical process is, we essentially create these bubbles in these very specialized detectors. So we had the proposal, what we want to do. Imagine you have a test object, this is your nuclear weapon. You have a neutron beam, and essentially we look at a radiograph of that object. And we now have sort of a full-fledged setup at the Princeton Plasma Physics Lab, where we sort of work with this and further develop and refine the protocol. And again, without going into too much detail, but fundamentally the idea here was, and still is, that at the end of the inspection, every detector has the same number of bubbles, if the weapon is authentic, plus minus Poisson noise, okay? And that's done by preloading the detector to different values, or the detectors. And if and only if you show me a valid item, a valid nuclear weapon, there will be no information in the detectors, because they all have the same number of bubbles. But only if you show me something else that has less, let's say, less plutonium or a different shape, you name it, there will be sort of information leakage, and I will clearly see that the image on the right is not Poisson distributed, right? So that's fundamentally sort of the idea that we are still pursuing, and I think it really shows some promise. But again, it's non-electronic and perhaps somewhat less interesting for many in the audience, even though I see another question in the back. No, the setup is so the question is about the setup and trust. We don't have to trust the setup. There are there's a neutron generator, but the fact that the neutron generator is operating is sort of the inspector can confirm with different type of detectors if they want to do. We would claim there's nothing that you have to trust. You do have to trust that the detectors are working. But again, here we would argue you can recompress them. You can actually even post-measurement confirm that these are working detectors. If you think something went wrong, you can step on them and essentially spill the liquid. So there's we believe, and I think in terms of red teaming, our sort of reviewers were in general quite sort of happy with sort of this approach. In terms of, yes, this is sort of a good idea to remove the electronics just from the critical measurement process. Obviously, we have electronics in other areas of the setup, but that's where we're less concerned about sensitivities and classified information.
When you say zero knowledge here, is there any cryptography involved, or is it really just all physics?
There's no cryptography. I mean, it's a zero. There is no, okay. There's what I skipped over is there is a zero knowledge sort of protocol involved, and friends at Harvard, Boaz Barak, that's sort of what he does for a living, and it depends on how we actually sort of trade the detectors beforehand in terms of have an interactive element to the inspection. And so I didn't actually say the word zero knowledge, but it's on the slide. But of course, it's also key. There's another example in which, in the interest of the time, I'm going to skip over, and Christoph. No, it's fine. If there's time at the end, we can come back. But a couple of years ago, we said, well, if authenticating and certifying the electronics is so hard, what if we just used very simple electronics? Think in our case, we said 6502 processor just to have something, 3,500 transistors. This thing has been produced 1 billion times. We can find them, new old stock in the warehouse. So no one, or the assumption was, since no one knew what we would be doing with them, we can be quite confident that there are no hidden switches, etc. And we made it work, and we had a talk at the Congress, I think in 2017, where we demoed this on stage. I still think it's interesting. I'm sure there's sort of other concerns in terms of hardware security. We talked about printable circuits. Could it be possible to actually print a 6502 or even a simpler circuit that could perform some of the relevant data acquisition and analysis? And maybe the answer is yes, but let me skip over it. and get to some more recent work. And again, I'm actually going to show, I'm not going to show the results because I think Johannes and others should do this, but I want to sort of highlight the Bochum experiment here in a minute. And the idea is, or the term of art that we're sort of starting to use, is virtual inspections. So, and let me sort of pivot slightly to a connected but somewhat different challenge in this space. And as so far, everything we've done was on site. You know, we have two-player game, adversarial, we have a host, the inspector, we don't trust each other. But we still came and visited and spent time together. And often these facilities are highly secure and very sensitive. So that has its own challenges. So clearly they are the gold standard for everything we do in this space, also for safeguards in the civilian area. But they are costly. I mean, that is one factor, but they are also considered intrusive, especially in the context that we're talking about today. So the proposition, and this is something, again, we started to work on just maybe a month ago, maybe a year ago, is this: can we physically separate the host and the inspector? Again, this is not, brand new, but it's interesting and new in this context. And the idea being that many concerns could be addressed, many concerns about intrusiveness if we separate both. And the question is, for example, the host could perform certain activities on site, and I'll get to that in a minute in the second example, while the inspector is watching the activities remotely and perhaps even influences or directs the activities from either offsite the fence, perhaps outside the facility, and maybe even abroad, right? Very simple proposition, but I think there's actually, it's an important one that hasn't been looked at in greater detail. And just to give one example, it's not just me who sort of brings this up. This is a report by the National Academies that was published last year, and you can read the title. And in the relevant section about capability needs for arms control, you can see it's exactly saying that these new treaties, and these new treaties would be treaties that capture or place limits on weapons in storage. And that's really, I think, the way we will be going with Russia, hopefully one day again, and also China possibly, and other weapon states. That such treaties would likely require access to storage areas, either directly or remotely. And I think, we talked to them many times. I think this is exactly what they had in mind when they wrote remotely here. And I will just notice Jill Ruby, who was the chair of that study, she is now the #1. She's in charge of all US nuclear weapons in DOE since she left that study and was appointed to that position. And Corey Hinderstein went into government as well. So this is now sort of very much a very high level sort of US thinking, I would say. Okay, so here's the question, and I hope this goes back to an earlier one from the audience. So here's another setup. Can we remotely confirm that a declared storage configuration, just be clear, remains unchanged? Let's say, we have an agreement. Both the US and Russia have thousands of nuclear weapons in storage. They're not part of New START, but we do want to sort of limit them. And that's a reasonable possibility, I think, for sort of a restart of negotiations or discussions between both sides. You say you have them in storage. We sort of want to have some reassurance. Can we come up with a mechanism to confirm this? When we were talking among the authors, we sort of realized this is not something that's just relevant perhaps for nuclear arms control. There's actually some other contexts where this could be equally interesting. And you have art storage. There's the Geneva Freeport I may have heard about, where apparently or supposedly there are more than 1,000 Picassos stored in not only Picassos, but more than 1,000 Picassos in a single facility, the largest museum that no one has ever seen. so hundreds of billions of dollars value. And the same is true for some other weird kind of situations. There's this one in gold storage in Manhattan, also several $100 billion, where Germany actually has quite a big chunk of that, its own gold. And there was some discussion, I think, during the Trump years to bring it back and so on. So, but clearly you have all your assets in a different place. You have no or very little access. So again, there may be actually a use case or a scenario where you want to have some confidence, and you can't trust, right, the surveillance cameras that anyone would use there. I mean, that is obviously sort of the key thing here. Coming a bit closer, I don't even know where this is, but probably very close to where we are right now, underneath. Okay, so this is our setup here at Bochum, where we said, okay, storage container with some drums, and these are our warhead storage containers. This has been ongoing for quite a few years, and I do want to acknowledge the partners. I mean, it's the folks here in Bochum, but also Uli Rührmeier at LMU and Munich. It's our team at Princeton. And collaborators of Boaz Barak and Gal Kaploon at Harvard. And I think I was hoping to say a manuscript under review or something, but I think we're pretty close to submitting this. And I don't know if everyone knows everything about this, but let me just sort of briefly run through the idea. So we have this room with our assets that we store there. In our case, just these drums. Supposedly they're very valuable. Perhaps they have warheads, even though some would argue warheads are not have no value. But we do introduce this challenge response generator that emits and receives radio wave signals, and there is complex multipath propagation providing unique and reproducible fingerprints of the configuration. Again, you know more about this really than I do, and some of what the technicalities are with regards to radio wave propagation, emission, and detection. Then there's a setup phase where the inspector actually creates a private dictionary of challenge response pairs. That's private, and it has to be somehow managed. Sort of to obtain this, but from then on, the inspector can query the room remotely, and correct answers can only be provided if the configuration remains unchanged. And that's what Johannes has been, working on for the past couple of years, I guess, by now. As I said earlier, I'm not going to show you sort of the results. They're all in the paper, but again, it should be Johannes and others to show them. But in a nutshell, I think what we show is that the room can't be manipulated without detection, sort of 3 mm displacements. The challenge space is large, so an adversary can't just measure everything and have answers available, even though the room no longer exists. Everything is public about this setup. The communication channels are public, and the hardware is not sort of certified, authenticated. We don't have to trust it. If you bend the mirrors, then it just won't work. But nothing secret about the hardware. Unfortunately, there is one inspector visit required during the initial setup phase. 0 would have been nicer, but I think so far we are down to 1. And in the paper, we show that the room can't be simulated, the room can't be cloned, and machine learning attacks that would aim at predicting future challenge response pairs based on previous known ones fail, and in any event would require very large training sets. So that's sort of another idea that we have been sort of pursuing in this space. And again, it's a broad collaboration between Bochum, Munich, Princeton, and Harvard. Okay, so that's sort of what I sort of want to do broadly cover. I have one more thing that again, it's very recent, and I don't have any results in a way. I should have given this maybe a year from now or so, but I'm actually quite sort of excited about this. That why not? Let's put it in there, because it's very much related to the previous problem. So again, the same setup. Can we remotely follow? And I promise you, I will finish in 5 minutes. Can we remotely follow certain allowed activities that the host performs? So the previous question was, we just wanted to confirm that nothing has changed. Obviously, it would be more interesting if the host would actually performing certain activities, maybe look at a serial number, we could remotely follow the activities. So obviously, you would think, well, video wouldn't be video the obvious use case here. And I think that's what the National Academy had in mind when they wrote, remotely. So what are the requirements here? So for me, at least, number one would be security and privacy. I think that's sort of always the killer criterion, because otherwise people won't even talk to you. So how can we follow relevant activities without, let's say, accidentally capturing additional information that is sort of also present but irrelevant for the task? That's number one. And, ideally, even an accidental sort of mistake that someone is making, moving the camera, it should not be able to leak information. Then there's a question about, how do we get the data out, transmitting the data from inside the facility to somewhere offsite when, everything's concrete and, 2-meter thick walls and so on. Data integrity, I guess that's something where your expertise would come in. Perhaps it doesn't have to be in real time. Again, this is something that one would have to think through. Could be recorded and then reviewed later, perhaps. And then finally, I would also add what has been called, live verify and local verify. And again, I'm sure this is something you think about in your for other projects too. How do you know it's actually being recorded as we speak? Is it a replay attack or not? Can I even be sure you're on the right location? Maybe you're in a completely different location and perform these activities, which could in many ways actually be an advantage, that I'm not actually able to know where you are. I may only care that it's live and it's real, and you may not want to reveal the location. I think that's possibly a big plus. Okay. So this is what I have for you. And the question is, what do you see? Hopefully nothing, except for maybe a hot or stuck pixel there on the left, but that's not all too relevant. It's actually, you should see there is some noise, but you can't see it here on the screen. But then something is happening, and you can see it here. There should be another event here on the left. And so this is actually video footage that I recorded, I think, exactly 1 week ago at TU Berlin with a colleague, Guillermo Gallego. So what is it? I mean, maybe some of you know this already. This is an event called event-based vision, or the original name for it was sort of silicon retina, an idea from the 90s, and Misha Mahowald was sort of the pioneer in sort of having the idea originally. It's now known, it has different names, and it's being commercialized now. So different companies try to sort of brand it with their own name. Event-based vision is one of them. Neuromorphic vision is another one. Bio-inspired vision, you name it, dynamic vision. But fundamentally, the idea is always the same, and it's sort of illustrated here on the right-hand side. And it means essentially trying to emulate how biology works, which is sort of very different from the way we have camera or use cameras today, which are frame-based, right? In reality, what biology does is, again, I don't want to get into too much detail, and I'm not a biologist. But we have obviously neurons in the retina, and they are not actually sensitive to light per se. What the neurons fire when there's a change in intensity, right? and they can either go up, so there was an intensity increase or an intensity decrease, but actually nothing happens when you look at sort of a constant image. It's like a flat field of view that is not changing. And all the neurons then eventually end up in the visual cortex in your brain, and that's where the image is assembled and essentially becomes what all of us see here. Why would you do that? Well, it turns out the bandwidth is much smaller, it's much faster, it's much more efficient, it's low power. And as you know, even an insect, like a fly is much more efficient in using vision than anything we can produce today in terms of real time and power consumption and memory and so on. So clearly the idea is this could be the future, especially for, let's say, robotic vision or so. That was what Misha Mahowald's sort of great idea was in 92. Unfortunately, she did take her own life a few days after her PhD, but everyone who worked with her says she was an absolute genius. It took 20 years basically to actually turn this into a real sensor, and only now these cameras are becoming available. And again, I highlighted some of the features already. Extremely low bandwidth. There's no redundant data. Only when a pixel changes is actually data is transmitted. Very low power consumption. It's asynchronous, so you're not frame-based. So you can actually have extremely fast response, typically in the microscale, on a microsecond scale, which is interesting if you're looking at fast sort of moving images. And the holy grail here, I think, is autonomous driving, where these cameras should perform sort of be very powerful in a way, in many ways. High dynamic range, and again, as I mentioned, they're just now becoming available. They're still quite expensive, but something that grant funding can provide. So here's the actual scene, and so we recorded both with the event-based camera and with a frame-based camera, and sort of you can see sort of my gimmick here. There's a secret in the back that was on the wall. The E equals MC squared. I mean, I couldn't come up with a more interesting secret, but the camera just can't see it. And again, there are certain challenges in making sure that you don't accidentally reveal the information. But so fundamentally, the idea is that the data was never on the sensor, right? And we should be able to sort of have confidence that the sensor itself never actually registered anything. And so there's nothing we have to sort of process and encrypt and sign and so on downstream if it simply wasn't there in the first place. Okay. So again, I think there are some opportunities to actually use this, building on this concept in sensitive facilities, not only for autonomous driving. Again, this is just really a quick demo. We would have to design the ConOps, the concept of operations around it. How would you actually use this in the field? I will also emphasize that, of course, what the community, everyone else except me, I guess, is trying to do the opposite. I mean, everyone would try to use event-based vision to reconstruct the image, and you can do machine learning, obviously, and so on. So you try to extract features from the events. That's where all the effort is going, 99.999% of the effort. So the red teaming sort of built in, right? I mean, we can always sort of go back and say, can you reconstruct the image from the data that I've given you? So we don't have to worry about that part. Okay, I think I'm done. In a nutshell, I think we had 25, maybe 30 years now of R&D in this space, and maybe I'm exaggerating just a little bit. I mean, I think we really haven't made much progress. We have not developed the technologies, the approaches that would be needed. I think personally, virtual inspection techniques will become increasingly important for different reasons. There's less trust today. It's harder to get into Russian, Chinese, US, French, whatever facilities, given where we are. I think also post-COVID, traveling per se is becoming sort of a less intriguing or sort of accepted, thing to do. So if we can do things remotely, I think will be actually a big selling point. And I do believe that there are some real synergisms between, your community, hopefully, and our community, where, thinking and just coming from different directions actually can produce some fascinating and new research. And with that, I think I'm done, and I'm happy to take questions if we do have the time.